us have been to inside 3D printing before? All right, looks like just about a third of us. And how many of us have been to an international show? One of the overseas ones? All right, got about 3 hands up. And just for my records, how many of you, or how many of us have bought a 3D printed good so far this year? All right, better than I was expecting, about half maybe. And finally, how many of us would feel comfortable making a prediction about what the 3D printing marketplace will look like in 2 years? Not a single hand. All right, we're going to try and change that here today. Presentation, reinterpreting hype and progress. I'd like to trace through some of what we've seen with the maker movement, talk a little bit about my background to give you some context, and also move forward really to the heart of the presentation, where we're going to talk about the future of the business models, the software, and the new machines that are coming out that are really going to transform how we're thinking about additive manufacturing. So to start, I'd like to take us back to 2007. And for me, this meant I was a senior in high school. But I read an article in Popular Science about Todd Lipson's desktop factory. You may have heard Todd speak, or maybe even shook his hand here earlier this morning. But I became infatuated with the idea of a machine that could build objects of any shape out of silicone or even chocolate. And so about a year later, I started building and became one of the first 300 people in the world to have a RepRap Darwin, the first printer of the RepRap project that has now spanned a huge number of machines on the market. And so that's a RepRap Darwin over there. And over here we have a fun time-lapse video of an Ultimaker I built a bit more recently, coming together. And what's amazing about the desktop market in part is just how many people it has exposed 3D printing to. I think if you look around the room, many of us have come from first being exposed to a desktop 3D printer and then exploring the more commercial machines as opposed to the other way around. And now I understand that there also are the experienced dinosaurs in the room, as Ian Gibson of Deacon likes to describe his class of 3D printers. But for many of us, desktop 3D printing really put the technology on the map and opened our eyes to how we can do more impressive things in metal, and it goes way beyond plastic and single materials. And so I've spent the last 2 years learning from the best. This is my 10th Inside 3D Printing Conference as of today. Over the past 16 months, I've visited 11 countries and done over 30 site visits, trying to visit and learn from some of the leaders in the space, like the General Electrics of the world, Shapeways, and ranging quite drastically depending on demographics. And this year I was privileged to be a contributor to the 2015 Woolworths Report, writing a section on China, where I spent about 6 weeks in 2014. So enough about me. I want to get on to the meat of the presentation, which is software and new machines and business models. And I put it in the order starting with new machines at the bottom, as I think that machines are really the foundation here. And moving a layer up, the software enables us to really take advantage of the machine's hardware, and surely there are limitations. We all know that a 3D printer itself is rather stupid. If you've watched a printer go, you might have seen some ranging from the trivial to the horrific print failures. I woke up one morning in particular, what I've been calling the 3D apocalypse. I just had a ball of plastic just all over my nozzle, just moving around, and it turned out that my 16-hour print, which I stopped monitoring at about 12 hours in the last 4 hours, just went mayhem. And waking up to that is never a pretty sight. And finally, I want to get back to business models, which is, I think, one of the reasons why many of us are sitting here in the business and investment track. And but to really start thinking about business models, we first need to have an understanding of how this S-curve is moving forward. And we need to understand, with a space that's changing as quickly as 3D printing, if our business models will be antiquated by a new wave. And so that's the information that I want to provide you with here today, to make sure that as you think about investing your time and energy and money and resources, that you're putting it in the strategic areas that are going to be riding the wave of 3D printing rather than crushed by the tsunami. We'll start with machines. And on machines, I want to first harken back to the personal computer. It's somewhat of an oft analogy, although I haven't heard it too much at this conference this year. We certainly heard it a lot in 2013 and 2014, with 3D printing being compared to the personal computer. And I'd like to bring up two small case studies. The first being the Xerox Star. Out of curiosity, how many of us are familiar with the Xerox Star? Wow, we got two, and I'm going to go with 2.5 hands there. Xerox Star was the first personal computer to come out of Xerox PARC, out of Palo Alto. And PARC was well known at the time for the Alto, this incredible machine that could do all sorts of futuristic applications like Ethernet networking and be wired directly to a printer and do what you see is what you get out of the editing. And the Xerox Star was really more than just a single printer. It was an ecosystem. And you couldn't just buy one workstation. You bought multiple workstations that came with a router. It was all connected via Ethernet, and there was a printer that came with it. So it was this all-in-one intensive office. And you see on this screen here that there are 6 or 5 applications plus this keyboard that are all going simultaneously. A lot going on for a machine in 1982. Really sophisticated ahead of its time. And the reason why you probably haven't heard of the Xerox Star is because 5 years earlier, there was another machine that came out. This was an Apple II. And the Apple II couldn't do 1/10 of what the Xerox Star could do. But the Apple II was affordable at $1,300 compared to $75,000. You could put many of these in office. And another piece here is that the Apple II allowed for 1 machine per person to be operating. And if you were a coder, you didn't have to wait in queue. If you were in the office, there was no having to worry about who could be using the machine. It was your machine, it wasn't a shared machine. And that becomes harder with the $75,000 machine. So moving to 3D printing, I'm going to try and draw a parallel here. And I don't mean to be projecting as to what the narrative will come out, but rather to explore and say, hey, can we look at what happened with personal computer and learn what might happen with Hewlett-Packard and Carbon 3D. So HP has tremendous technology that we've learned about here today. And both of these companies are promising to speed up 3D printing by somewhere around 25 times the current rate. And this is exactly what this industry needs to move forward. The part here that I think HP needs to look at and learn from with the case of Xerox is that the top and the bottom are meeting right now. And the capacity of desktop printers to do interesting, complex, and sophisticated applications is drastically increasing, and it's increasing almost overnight. And so I think part of the lesson to draw here is not that HP is going to be the Xerox of 3D printing, because I don't think that's going to be the case, but rather that there is going to be a battle between these high-end commercial machines and the desktop machines underneath. They are both. The Carbon is going to go up in terms of functionality, as we're seeing. The desktop printers are going to eat away at the commercial from the bottom up, and the bigger guys are going to eat away at desktop from the top down. And here's how each of those cases might work. From the top down, we have service bureaus, right? If my goal as a consumer is to get a 3D printed part, I would argue that I don't particularly care how it was made. And in fact, I really don't like burning my hands on the nozzle of the whatever desktop 3D printer is currently in my home. And I don't particularly like going through the process of unjamming it, or doing the horrible process where my printer gets jammed and I have to hold a wrench and do a live heated unscrewing so I can pull out the clot. And I'd say probably 1 in 3 times I burn my thumb. Now that's not a particularly enjoyable experience. I don't look forward to it. Even as much as I love using 3D printers and the magic of having materialize in front of me, if I could, for a similar price, just go to a service provider and get that done and delivered to me in a short fashion, say intraday even, I would much rather do that. And that's the type of world that I think an HP printer can start to provide. You can imagine a bunch of these things sitting in an Amazon warehouse or FedEx or UPS. And with the print speeds that they're talking about, the same-day delivery is not something that is of dreams. Having something manufactured locally, delivered that same day, how fantastic. And I think that's a world that the HPs of the world are going to be able to enable. On the flip side of the Carbon 3D model, we have a very different paradigm. And this is very much the 3D printer in every home paradigm, or perhaps even the larger networks of smaller printers that are scaling in parallel as opposed to singular units that are manufacturing. So which way this narrative will go is, I think, an open question. And I referenced the personal computer Not to say that I'm going to pick a horse to win here, but rather to say that these are some of the themes that you might want to think about as you try and understand what's going on in the desktop world, what's going on in the commercial world, and how the two worlds will be colliding. And it's not just plastics that are seeing these speed increases. With metals, we're seeing tremendous improvement as well. This part behind me is a 3-meter long wing spar printed in titanium by Bright Laser. And stupendously, it was printed in 2 days. I was stunned when I heard that. Because prior to my visit, I had been speaking with a Boeing executive, a senior executive, and asked them how long that part would take them to make, what the lead time would be. 12 months. Wow. Granted, there was about 28 days of post-processing time to getting the layers down, and they did not need to do any HIPS process for improving the fatigue of the part. But this part has been installed in a C919 passenger aircraft, which is China's first passenger plane. It's still an open question if this will be going into every plane, as with China's first aircraft, there are a number of considerations going into it to try and de-risk the situation. But this technology is coming, and being able to print metal at this scale and this speed is game-changing. I don't have a slide for this, but they've also mobilized this technology and put it in a truck that can travel around and drive up to a large metal part and do repair work directly on it. I should mention that this is a directed energy deposition process, which many of you may not be as familiar with as the standard TLAs, the 3-letter acronyms that surround us in 3D printing, or 3DP, keep on that theme. And it uses a powerful laser that creates a melt pool on a metal, and then it blasts powder down at it. And much of the powder goes off, but some of it sticks. And so you can see how the deposition rate can be drastic because you can just continue blasting higher rates of powder and increasing the melt size. And so I want to touch on something else here, which is, so 25 times is sure interesting, but it'll be really great 100 times faster. And up until this conference, I hadn't really heard about people talking about 100 times faster, but I've been pleasantly surprised to see that people are thinking beyond the current S-curve in technology and asking, well, what comes after this S-curve in 3D printing, and how might we be able to go 100 times faster? And I'm convinced that the answer to this is that it is possible, and that continuous production is the way to do it. So here's an old picture from the Ford assembly line, the Model T. And what's crucial here is something that we need to get away from with 3D printing if we want to go 100 times faster, which is this process of doing parts in batches. And something that is being ignored when you hear this figure that I've said a couple times now, 5 times faster with HP and Carbon 3D, is that these considerations, calculations, don't really take into account setup and teardown time. The cleaning time, how long it takes to remove the batch and post-processing. It's really only in the actual fabrication and not all the other nitty-gritty, more labor-intensive details that are kind of the dirty secret of 3D printing, the technology that's promising to remove labor. And so what I imagine a continuous production to look like in an optimal case, I'll give an example for HP first. Rather than putting a bed and doing it parallel to the ground, you can have just as easily the coder do it at an angle. It doesn't have to be flat. You can have it coated at an angle. It doesn't matter if it's 30 degrees, 45 degrees, whatever the powder will support. And then likewise, have the inkjet heads go at an angle, and have the platform sitting on a conveyor belt, such that you have a big old, if this is my conveyor belt here and it's printing this direction, that side of the table, you have finished parts that are coming off. And in this same machine, you can depowder, you can suck it out, you can recycle it. On the flip side, you have the parts here that are starting to come out. So that's one example of continuous production. And there's other examples you can think of for other technologies. You may have seen Project Aura, the collaboration, the ill-fated collaboration with 3D Systems and Google that got the cord pulled on it. But still was an interesting technological approach of doing multi-jet modeling, or their version of polyjet, we're familiar with the object systems. And using a conveyor belt that's moving around in circles, and you have all the heads distributed, and they are just trying to optimize how much of the liquid they can have just flowing through there. So if you were to flip that on its head, and instead of doing it in a circle, and just do a continuous line, like an assembly line, you can imagine how for a given Z height, that every single part coming off of it every couple seconds could be a different part. The challenge here is that you need the demand. You need the demand to justify a multi-million, $10 million plus investment in order to make this type of factory. So when I think about continuous production, how to make 3D printing 100 times faster, this really harkens back more on the HP model, as I don't see it being possible on the desktop model to make it 100 times faster, at least today. I don't think the replicator in the Star Trek sense is feasible in the next 10 years. Beyond that, I hesitate to wager a guess, as who am I to say what is possible 20 years from now. But I think that it is possible in the next 10 years to have the process 100 times faster by doing a more manufacturing approach and by doing this type of scale. So let's move on to software. And software is, we're going to do a little dive in here. But first I want to start by examining a part by nervous systems. And this is a gorgeous 18-karat bracelet that was printed in one go on an EOS M80 Precious. This is at the, I think, Inside 3D Printing Santa Clara conference this was shown. And it's an incredible part. Well, there was some polishing done, so some post-processing, but all these pieces are interlocking. And the software behind this is magical. They didn't have to design each joint by hand and put it in there, but rather the software automates this process. And it allows the user to customize the shape and the number of triangles and the pieces there. And so this is an example of parametric modeling. Modeling that isn't based on an STL file. And hold your breath, it's going to be okay. We're going to take a look at what an STL file actually looks like. For those of you that haven't right-clicked on it and opened it in the text editor, because why not? If the STL file hasn't been formatted in binary, it is in ASCII, here's what you'll see. And this is really the core right here that we're interested in. It defines 3 vertices, and each of these vertices is, the combination of the 3 is a triangle. And so an STL file is made up of thousands of these, depending on the file complexity. And the greater you want the file to actually mimic the real world, the more triangles you need. And ultimately, you can get to a high enough point, probably somewhere in the millions of triangles, where it's close enough that if you're going to throw it out on a 3D printer, you're not going to be able to make out the triangles. But rest assured, any part you're looking at, when it went through the printer, has got a bunch of triangles that have been translated into G-code. Now I'm going to compare that to a more parametric approach. And so in the parametric approach, we have, it's more like a programming language, if you will. So I have a cylinder, and I have this h variable for height, and I define it as h1. And r radius is r1. If I wanted to change the height of this, it would be as simple as having the program change this single variable, and bam, the cylinder height has been adjusted. The contrast in the STL file, it would be a laborious and horrible process in order to update all of these vertices if you wanted to make these triangles greater, or add more triangles onto it. So you can see how this type of equation allows for new types of parts. And it's not just humans specifying the parameters, there's also machines doing optimizations. So this is an example of a part. This is done by Euphoria. And this is a great example of topographical optimization. So this part has had about, I think, a 40 to 50% weight savings in terms of the original part that it was replacing. And what we see here is this beautiful structure of little bubbles, this kind of web that connects everything together. And this was not done by hand. It would be horrific to do by hand. It would take hours and hours and hours, and it wouldn't be feasible. Instead, this is a new paradigm for design, the one that I'm really excited about. Rather than going in and having to design the part by hand, and then evaluate in testing, whether in software simulation or in actual printing, iteration, and physical mechanical tests. Instead, the designer informs the computer what the requirements are. We know that we need this circle up here, we know that we need that guy over there, we know that these 3 pieces have to be connected, and that it can't go beyond a certain bounding box. And we can give other specifications too. We can say that, well, not only that in terms of design, but we have some constraints in terms of what the machine can do. So we can't do holes smaller than a certain size. So don't generate any of those. And the software can go through and do an approach like a genetic algorithm in the case of Grasshopper. And essentially what it's going to do is it's going to take all these parameters, it's going to make random permutations to them, it's going to slightly adjust this H value, and then it's going to go through a software simulation and test. And it's going to say, oh, this value was slightly worse than the last value, let's go the other direction. Or maybe there's other more intelligent ways of going about it that allow for more random sampling in order to arrive at an optimal result. What's crazy about topographical optimization is that this used to be a fantasy land in the mathematical world. And so I'm applied math and economics by academic training, so you can hear my geekiness coming out here. But it's amazing to see this niche field that was kind of this engineer dreamland that has now become a reality because of the technology that we have. And now the software has to catch up because most of the design engineers that are trained aren't used to doing this type of design approach. And it's not necessarily plug and play to switch over to this new paradigm. It really requires a new piece of education, a new piece of training. Another example is this is a piece from a NetFab, and you see a similar type of paradigm. Here, what I really like about this part is you can see the internal lattice structure. And this is starting to happen more and more as the metal printing is more sophisticated. So we're starting to understand enough about the thermal gradients involved in the process in order to robustly and repeatedly print out a lattice structure to save weight internally in the part and to optimize strength really only where it's needed and to try and avoid doing it all over the place. And finally, I want to touch on 3D scanning. So this is a 3D scan selfie that I got from a place called Elite Robotics. And while I don't think that 3D printing selfies are going to become the next Instagram, I do think that it's interesting to try and think about how the world changes when you can really scan the things around us. So if you think about, I have this situation on a regular basis when I'm traveling and living. I have something that breaks, and I think to myself, oh my God, I can 3D print this. This is going to be great. But that sits on my to-do list for a little while because it's not super high priority. And I realize that it's going to be, it's going to take me about 8 hours to do it, and man, it'll be awesome when I can put up this part that I 3D printed up on the slideshow of my presentation. But it doesn't tend to happen, mainly because it's a pain in the ass to take a broken part and to actually get it fixed. I might fix that part one time, invest 10 hours of my time, and there you go, I saved $13. or maybe it was a chair or something, or some other part that would have been easier for me to replace the whole thing rather than replace a little part. But I think that equation starts to change with 3D scanning. When you have the tool set to be able to quickly, maybe even using your phone with the stereoscopic cameras that are coming out, like Intel RealSense and Apple's acquisitions, in 2 to 3 years, we're going to have tens of millions of consumers walking around with a 3D scanner in their pocket. I happen to have a 3D scanner in my laptop bag, but that's because I like doing show and tell, and less because I need it all the places that I go. But I think that once it is ubiquitous, that it will become a powerful technology allowing us to digitize our world and to let the consumers gain access to all these amazing capacities that 3D printers can do, but practically don't today, mainly because consumers don't have time. So business models. Business models is a whole can of worms that we can spend weeks and months talking about. So I'd like to start just by giving a short narrative, a story that I find particularly powerful and exemplifying. I'd like you to meet Asher. And Asher is 9 years old and got incredibly excited when he learned that for the first time in history that Hanukkah and Thanksgiving were on the same day. So he dreamed up the monarchy. Part turkey, part menorah. The monarchy went on to a $50,000 Kickstarter campaign. A 9-year-old boy launching a manufacturing business, unthinkable even a decade ago. And it just gives me shivers to realize that these are the types of tools that we're putting in the hands of a generation that aren't told that this is a toy. And when you don't tell someone that something is a toy, right, just look at what can happen. So I love the story of Asher because it does combine a couple of threads here, which is that 3D printing has this underlying technology, that of the internet, and that of all this social change that's going on with the maker movement. It's more than just a technology. It really is this platform for bonding, this platform for relating, this platform for making manufacturing more human. And on this topic, after I gave this talk at a university in Rhode Island, this person in the audience came up to me and pulled out of his ear this hearing aid. And I knew that a bunch of hearing aids were 3D printed to the tune of millions of units to date, but I didn't quite understand the meaning of that. And so he calmly explained that previously his hearing aids were made out of some sort of foam and that the electronics was in, and it didn't fit particularly well. When he would work out or get sweaty, it would kind of fall out of his ear. He could wear it in the rain, but he couldn't go swimming with it because it could be damaged. And that when he got his 3D printed hearing aids, that they were completely waterproof. Electronics were sealed in, it fit his ear perfectly, it didn't fall out anymore, it improved his ability to hear. Just remarkable. And I also want to segue this to understanding the world of the long tail. As we talk about the long tail a lot, and I want to propose that the long tail is actually superseded in some ways by what I'm calling constrained customization. So in a long tail application, the classic example might be Amazon with books. So Amazon has many SKUs. And so Pareto's law, if you're familiar with it, says that 80% of revenue comes from 20% of products. And what we saw with Amazon and with book selling is that when the number of SKUs, the number of units available, drastically increased, that this equation shifted downward. It became more like 20% of products were generating 60% of revenues. So I want to point out there is that it's still a relatively small portion of the products that are generating the majority of the revenue. The long tail is still important though. But what I mean by constrained customization is that here is a hearing aid where everyone's hearing aid is slightly different. Technically a different SKU, but to the consumer, we all perceive this as a single product, right? He's going to get one hearing aid, it's going to be customized for him, and every hearing aid might be different, but it is still the same product from the customer's experience. The customer goes to the same company, goes to the same brand, and buys it. So that's what I mean by constrained customization. So rather than thinking about the long tail, where I think it's been quite difficult to actually realize connecting, it's not so much supplying the long tail with demand, but actually connecting the demand to the supply. Connecting the person that wants this weird niche object, he doesn't even know that 3D printing is an appropriate solution for him. How is he ever going to find that that good exists? Whereas with constrained customization, you go to the brand, you go to the experience, and it is customized either automatically based on biometric information, or perhaps more hand-holding, like what you might see with Nike ID with doing sneakers. And what we see with this is that hearing aids are only the beginning, and the dominoes have been falling for some time now. I think a watershed moment was when GE announced that the LEAP fuel nozzle will be 3D printed, and that they're going to do it with 20,000 units a year. They're going to be buying 100 plus metal 3D printers. Airbus has made similar announcements. I'm sure Boeing is doing something of the same sort. And this is for individual product categories. And so I think today, it really looks like discrete dominoes are falling over. But when we look back in hindsight, we're going to see that it looks like a blur, and that it seemed to happen overnight. And just here, standing here in the moment, when we have the latest piece of news to talk about, it doesn't feel like it's moving quite as fast as the industry is. With this domino effect has come not just the good, but I would call it the bad. And this is Attack of the Clones. There are over 700 companies that make 3D printers. 700 companies. 95% of them can't survive. There's not room in the market. And it saddens me to see so many people going after the same RepRap-derived FDM product. And what I try to tell people when I come across this is I say to them, one, please don't worry that I'm saying that what you've done has been a waste of time. Because I did something similar with building a printer, and I had tremendous experience. By building your own printer, you get caught up to speed with the status quo in FDM, and that's a great experience. But you need to use it as a springboard to do something after that, to do something more innovative. Because they're just, with these types of FDM printers, they're going to be antiquated by the S-curve that's coming technology. They're going to be antiquated by companies like HP, like Carbon 3D. And so if you're not anticipating that and trying to come up with a reason why your printer should be in the marketplace, not just today, but in 5 years from now, it's important to take a step back and try to qualitatively assess where your vision of the 3D printing market is, not just where your vision is of your own company. And this is a narrative that's been circling around, that of, will a 3D printer be in everyone's home, or will it exist in the cloud? Well, we just heard from Jonathan in the MakerBot keynote that he's of the belief that it will be in every home. And we hear from others that are maybe more on the service bureau side, unsurprisingly, that it's really going to be in the cloud. I haven't made up my mind yet, but I sure know that it's unlikely that we're going to see desktop printers as they look today in everyone's home. I just don't see a case for it. It very well might be that there are very good applications, like education, for example. When I have kids, I would love for them to grow up using a 3D printer from a young age and just knowing that they can be empowered to dream something and to create it, rather than just sketch it and to see it in their head. As learning that skill of executing, of taking an idea and actually putting it into the physical world is such an empowering one, and such an important one to know that you can do. With the cloud, though, this really starts to touch on distributed manufacturing. Excuse me. So 3D printing is undoubtedly a force for decentralizing manufacturing. We're moving from this distant web of global factories back to local production. We saw with the case of Boeing outsourcing the 787, which was supposed to be the triumph of global supply chains, of leveraging and of hedging different costs in different regions, of using labor where it was cheapest and using materials closest to the source. And we saw this all cascading down into horrific design problems and a plane that was so long delayed that any of those cost savings were quickly evaporated. And I think that 3D printing helps us move back towards the direction of localized production. And I imagine that most of us would agree with that. The part that, and here's the rub really, is will it be in everyone's home? And I argue that it may not be in everyone's home in terms of the mass consumer, even though it may be a mass device. And here's why. There will always be economies of scale in logistics. If I want to produce 1 million unique parts, it will always be more efficient for me to do that in one location than 1 million disparate locations. Think about the stocking of materials. Think about any sort of post-processing that might be involved. Think about just the different sizes and shapes and environments and machines that you will need. 3D printing really is this umbrella phrase that refers to a multitude of technologies. It's not like there's one 3D printer out there that I can point to in the designer expo hall and say, yes, that is the 3D printer. That is one of these 100, and that one's more like that one, but totally different from that one. So I think the idea of a 3D printer being in every home may happen, but I don't think it's going to look like the replicator of Star Trek. I think it'll look more like the kitchen robot that is printing your food and adding in the proper micronutrients, or maybe even the medications that you need. I think it'll look like it'll be in the person's house next to their wood shop and be used by the makers of the world that are really about doing more hands-on engagement with the objects and things that they own. So if you're someone that does your own plumbing, I think it'll be someone who's a 3D printer. If you're someone that would rather hire somebody to do that, you're probably going to buy it from the service bureau. So the ultimate promise of 3D printing, I want to come back to the cost equation though. So here's a generic equation for the cost of a good, well oversimplified. But 3D printing erases the labor component here and makes it so that you presumably only pay for the design, the energy cost, and the raw material. And I bring this equation because it really isn't static and the narrative hasn't been decided yet. The part I want to point out is that design, it's not clear if the cost of the good is going to include design. I know that's a kind of a crazy thing to say, but I'd like to point to Napster and point to what's going on. Is anyone here familiar with popcorn time, out of curiosity? Oh, one hand, cool. Good on you if you aren't. Popcorn time, but although you should. Popcorn time is Netflix for all movies. It's a piracy app that allows people to stream any movie on demand, 1080p, in real time, short setup. It's a better experience than any paid app out there. I can pay for HBO Go, I can pay for Netflix, I can pay for Amazon Prime, I can pay for everything under the sun, but I can't get as good of an experience. And there's a lot of people, especially in the maker community, that don't believe that they should pay for design files. I'm just stating it how it is, having interacted. And part of the mindset is that of open source, and that of contributing back. And part of it also, again, comes a little bit from Star Trek, which has a very Marxist underpinnings to it. And so, yeah, here's some chuckles from people that are more familiar with the show. And what we see is that there's a belief that producing goods shouldn't cost anything other than what I need to actually do it. And this, of course, ignores the design component, and it doesn't respect the fact that if we want to incentivize the adoption of the technology, that we need to pay designers and make sure that they're compensated. So this is a scary one for me, where I think about it, it's up to the industry to do this right. Right now, when you buy a product and you pay for design, you buy a good, and that design price is included in the good. and you're not aware of how the price breaks down. Well, 3D printing is explicitly a separate thing that you are paying for. And as soon as you break it out that way, people start asking, well, why do I need to pay for this when it's digital information? I'm used to getting digital information for free. So this is a piece that we need to grapple with as an industry and figure out the right model to properly compensate designers while understanding that there is this huge force, at least from the bottom up, saying that we're not interested in paying for designs. So I'd like to end with a thesis, which is that new machines, software, and business models enable 3D printing to cross the chasm behind the scenes within 2 years. And I'd like to take one more round of hands. Just curious, is anyone here more confident now in making a prediction about the future in 2 years? Man, I guess I should stay up here a little longer. Thank you.